In mathematical analysis, a measure on a set is a systematic way to assign a number to each suitable subset of that set, intuitively interpreted as its size. In this sense, a measure is a generalization of the concepts of length, area, and volume. A particularly important example is the Lebesgue measure on a Euclidean space, which assigns the conventional length, area, and volume of Euclidean geometry to suitable subsets of the n-dimensional Euclidean space Rn. For instance, the Lebesgue measure of the interval 0, 1 in the real numbers is its length in the everyday sense of the word. Specifically, technically, a measure is a function that assigns a non-negative real number or plus infinity to subsets of a set X. It must assign 0 to the empty set and be additive. The measure of a large subset that can be decomposed into a finite number of smaller, disjoint subsets is the sum of the measures of the smaller subsets. In general, if one wants to associate a consistent size to each subset of a given set while satisfying the other axioms of a measure, one only finds trivial examples like the counting measure. This problem was resolved by defining measure only on a sub-collection of all subsets, the so-called measurable subsets, which are required to form a sigma algebra. This means that countable unions, countable intersections and complements of measurable subsets are measurable, non-measurable sets in a Euclidean space, on which the Lebesgue measure cannot be defined consistently, are necessarily complicated in the sense of being badly mixed up with their complement. Indeed, their existence is a non-trivial consequence of the axiom of choice. Measure theory was developed in successive stages during the late 19th and early 20th centuries by Émile Barral, Henri Lebesgue, Johann Radon and Maurice Fréchet, among others. The main applications of measures are in the foundations of the Lebesgue integral, in Andrei Kolmogorov's axiomatization of probability theory and in ergodic theory. In integration theory, specifying a measure allows one to define integrals on spaces more general than subsets of Euclidean space. Moreover, the integral with respect to the Lebesgue measure on Euclidean spaces is more general and has a richer theory than its predecessor, the Riemann integral. Probability theory considers measures that assign to the whole set the size 1, and considers measurable subsets to be events whose probability is given by the measure. Ergodic theory considers measures that are invariant under, or arise naturally from, a dynamical system. Definition: let X be a set and sigma a sigma algebra over X. A function mu from sigma to the extended real number line is called a measure if it satisfies the following properties: non-negativity, for all E in sigma, mu0, null empty set, mu equals 0, countable additivity, for all countable collections of pairwise disjoint sets in sigma. One may require that at least one set E has finite measure, then the empty set automatically has measure 0 because of countable additivity, so, if only the second and third conditions of the definition of measure above are met, and mu takes on at most one of the values plus or minus infinity, then mu is called a signed measure. The pair is called a measurable space. The members of sigma are called measurable sets. If and are two measurable spaces, then a function is called measurable if for every y measurable set, the inverse image is x measurable, i.e., the composition of measurable functions is measurable, making the measurable spaces and measurable functions a category, with the measurable spaces as objects and the set of measurable functions as arrows. A triple is called a measure space. A probability measure is a measure with total measure 1, i.e., mu equals 1. A probability space is a measure space with a probability measure. For measure spaces that are also topological spaces, various compatibility conditions can be placed for the measure and the topology. Most measures met in practice in analysis are Radon measures. Radon measures have an alternative definition in terms of linear functionals on the locally convex space of continuous functions with compact support. This approach is taken by Bourbaki and a number of other sources. For more details, see the article on radon measures. Examples. Some important measures are listed here. The counting measure is defined by mu equals number of elements in S. The Lebesgue measure on R is a complete translation invariant measure on a sigma algebra containing the intervals in R such that mu equals 1, and every other measure with these properties extends Lebesgue measure. Circular angle measure is invariant under rotation, and hyperbolic angle measure is invariant under squeeze mapping. The Haar measure for a locally compact topological group is a generalization of the Lebesgue measure and has similar uniqueness properties. The Hausdorff measure is a generalization of the Lebesgue measure to sets with non-integer dimension, in particular, fractal sets. Every probability space gives rise to a measure which takes the value 1 on the whole space. Such a measure is called a probability measure. See probability axioms. The Dirac measure delta A is given by delta A equals chi-s, where chi-s is the characteristic function of S. The measure of a set is 1 if it contains the pointer and 0 otherwise. Other named measures used in various theories include Borel measure, Jordan measure, ergodic measure, Euler measure, Gaussian measure, Burr measure, radon measure, Young measure, and strong measure 0. In physics, an example of a measure is spatial distribution of mass, or another non-negative extensive property, conserved or not. Negative values lead to signed measures. See generalizations below. Liouville measure, known also as the natural volume form on a symplectic manifold, is useful in classical statistical and Hamiltonian mechanics. Gibbs measure is widely used in statistical mechanics, often under the name canonical ensemble. Properties. Several further properties can be derived from the definition of a countably additive measure. Monotonicity. A measure mu is monotonic. If E1 and E2 are measurable sets with E1, E2 then measures of infinite unions of measurable sets, a measure mu is countably subadditive. For any countable sequence E1, E2, E3, of sets n in sigma, a measure mu is continuous from below. If E1, E2, E3 are measurable sets and n is a subset of n plus 1 for all n, then the union of the sets n is measurable. And measures of infinite intersections of measurable sets, a measure mu is continuous from above. If E1, E2, E3 are measurable sets and for all n, n plus 1 n, then the intersection of the sets n is measurable. Furthermore, if at least one of the n has finite measure, then this property is false without the assumption that at least one of the n has finite measure. For instance, for each n, let n equals n infinity r, which all have infinite Lebesgue measure, but the intersection is empty. Sigma finite measures. A measure space is called finite if mu is a finite real number. Non-zero finite measures are analogous to probability measures in the sense that any finite measure mu is proportional to the probability measure. A measure mu is called sigma finite if X can be decomposed into a countable union of measurable sets of finite measure. Analogously, a set in a measure space is said to have a sigma finite measure if it is a countable union of sets with finite measure. For example, the real numbers with the standard Lebesgue measure are sigma finite but not finite. Consider the closed intervals k plus 1 for all integers k. There are countably many such intervals, each has measure 1, and their union is the entire real line. Alternatively, consider the real numbers with the counting measure, which assigns to each finite set of rails the number of points in the set. This measure space is not sigma finite, because every set with finite measure contains only finitely many points, and it would take uncountably many such sets to cover the entire real line. The sigma finite measure spaces have some very convenient properties. Sigma finiteness can be compared in this respect to the Lindelof property of topological spaces. They can be also thought of as a vague generalization of the idea that a measure space may have uncountable measure. Completeness. A measurable set X is called a null set if mu equals 0. A subset of a null set is called a negligible set. A negligible set need not be measurable, but every measurable negligible set is automatically a null set. A measure is called complete if every negligible set is measurable. A measure can be extended to a complete one by considering the sigma algebra of subsets Y which differ by a negligible set from a measurable set X. That is, such that the symmetric difference of X and Y is contained in a null set. 1 defines mu to equal mu. Additivity. Measures are required to be countably additive. However, the condition can be strengthened as follows. For any set I and any set of non-negative define. That is, we define the sum of the to be the supremum of all the sums of finitely many of them. A measure mu on sigma is kappa additive if for any lambda less than kappa and any family, alpha less than lambda, the following hold. Note that the second condition is equivalent to the statement that the ideal of null sets is kappa complete. Non-measurable sets. If the axiom of choice is assumed to be true, not all subsets of Euclidean space are Lebesgue measurable. Examples of such sets include the Vitali set, and the non-measurable sets postulated by the Hausdorff paradox and the Banach-Tarski paradox. Generalizations. For certain purposes, it is useful to have a measure whose values are not restricted to the non-negative rails or infinity. For instance, a countably additive set function with values in the real numbers is called a signed measure, while such a function with values in the complex numbers is called a complex measure. Measures that take values in Banach spaces have been studied extensively. A measure that takes values in the set of self-adjoint projections on a Hilbert space is called a projection-valued measure. These are used in functional analysis for the spectral theorem, when it is necessary to distinguish the usual measures which take non-negative values from generalizations. The term positive measure is used. Positive measures are closed under conical combination but not general linear combination, while signed measures are the linear closure of positive measures. Another generalization is the finitely additive measure, which are sometimes called contents. This is the same as a measure except that instead of requiring countable additivity we require only finite additivity. Historically, this definition was used first. It turns out that in general, finitely additive measures are connected with notions such as Banach limits, the dual of L infinity and the Stonechek compactification. All these are linked in one way or another to the axiom of choice. A charge is a generalization in both directions. It is a finitely additive, signed measure. Bibliography. Robert G. Barthold, The Elements of Integration and Lebesgue Measure, Wiley Interscience. Bauer. Measure and Integration Theory, Berlin. De Gruyter, ISBN 978-3110167191. Baer, H.S. A Primer of Lebesgue Integration, San Diego. Academic Press, ISBN 978-0120839711. Bogachev, I. Measure Theory, Berlin. Springer, ISBN 978-35403454138. Bourbaki, Nicholas, Integration I. Springer Verlag, ISBN 3-540-41129-1. Chapter 3. R.M. Dudley, 2002. Real Analysis and Probability. Cambridge University Press. Folland, Gerald B. Real Analysis. Modern Techniques and Their Applications, John Wiley & Sons, ISBN 0471317160. 2nd edition. D.H. Fremlin, 2000. Measure Theory. Torres Fremlin, Jet, Thomas, Set Theory. The Third Millennium Edition, revised and expanded, Springer Verlag, ISBN 3-540-44085-2. R. Duncan Luce and Lewis Narens. Measurement, Theory of the New Palgrave, A Dictionary of Economics. 3 pp. 428-32. M.E. Munro, 1953. Introduction to Measure and Integration. Addison Wesley. K.P. S. Bhaskara-Rao and M. Bhaskara-Rao, Theory of Charges. A Study of Finitely Additive Measures. London. Academic Press. pp. X + 315. ISBN 0-12-095780-9. Shilov, E. and Gurevich, L. 1978. Integral, Measure, and Derivative. A Unified Approach. Richard A. Silverman, trans. Dover Publications. ISBN 0-486-63519-8. Emphasizes the Daniell integral. Teschel, Gerald. Topics in Real and Functional Analysis. Terence Dow, 2011. An Introduction to Measure Theory. American Mathematical Society. Nick Weaver, 2013. Measure Theory and Functional Analysis. World Scientific Publishing.